In this video, we will talk about sequences. So, starting with the definition of a sequence. Well, the sequence is just a list of numbers, okay, in a specific order. Okay, we can usually we use the following notation: a sub 1, a sub 2, a sub 3, and so on, to denote the terms of the sequence in this order. So the first term or the first number usually is a1, the second one is a2, and then it's a sub 3, and so on. For each positive integer n, now here, for every positive integer n, which means for every n, when I say positive integer, that means I'm considering the values n equal 1, 2, 3, and so on. We have a specific number an. So you can always treat this as a function. Okay, so let's say this is the n natural numbers, positive natural numbers. Well, actually, just the positive natural numbers. So usually we denote it by z plus, since n contains 0. So you have the numbers here 1, 2, 3, 4, and this goes all the way to infinity. For each number here, I assign a sub 1. So I assign a number an. Okay, so for number 1, I assign a number a1, which we call the first term. For number 2, I assign a number a2. For number 3, a3, and so on. Okay, so it's really helpful to think of an as a function. Okay, so it's a function of the form a equal a of n, but instead of using the notation a of n, we use the notation a sub n. Okay, so for example, let's say that you have the function or the sequence is defined by the following: a sub a of n, I'm going to use a of n now, equal to n to the power 2 plus 1. Okay? So this is the same as saying a sub n equal to n squared plus 1. So we treat these the same, but this is the most common notation. Now this means the following, that if you want to find a3, for example, this is the same as a of 3, which means you substitute n by 3 in the given formula. So 3 squared plus 1, let's say here, and that's equal to 10. Okay, so again, the sequence can be thought as a function, but the domain of this function is the positive integers. Now the range could be many things. So here are some examples. I'm providing here a sequence, and the sequence, most of the times it will be represented by a formula. As I said, it's a function, so it will be well defined. And here I'm listing the first few numbers in this sequence. So if a sub n is equal to n, then a1 you just replace. So if I want here a sub 1, this is just 1. You are, whatever you put for n here, you're gonna put for the n here in the formula. So if I want to find a2, then this is going to be just 2, and so on. So you can see the terms here. Here's another example. b sub n, that's another sequence. So this is like another function. Now the answer is always 0. So no matter what n is, you're going to get 0. So this is like a constant sequence, and all the terms are equal to 0. This is another example. C of n equal 1 over n. Again, you replace n by 1, 2, 3, 4, and so on. Okay. Here's also another example. So you can see how this works. You can see that it's possible that you're going to have always positive. Maybe sometimes you get the same number. Maybe sometimes you get fractions. Sometimes you get negative. Sometimes it will alternate between negative and positive, as you have in the example of Dn. So we say that the sequence, so we use this notation an equal 1 to infinity, or sometimes we just use an, or sometimes we just use a sub n. All these will mean the same thing, means that I'm considering a sequence, an infinite sequence of terms a1, a2, all the way indefinitely. I say that the sequence converges to a limit L if we can make the terms an as close as we like to L by taking n sufficiently large. Now, this is not the formal definition. Okay, but this is the intuitive definition that you will take. I mean, the formal definition uses a different type of limit that you haven't, different definition of limit that you haven't seen in Calculus 1. If you're interested, you can take a look at the book about the epsilon delta definition. But for now, you just need to understand the following. I say that limit of an when n approaches infinity is equal to L if, let's say I have the following, L is this number. Okay, let's say this is the level L. Now you can have terms of the sequence at the beginning going up, going down, going up, going down, and so on, because remember the terms of the sequence are just some numbers. But what I care about is that when n is sufficiently large, okay, so when n is large here, then I can see that the behavior of these numbers are very close to L. In this case, I say that the limit of an when n approaches infinity is equal to L. Now we have a very important question here. How are we going to evaluate these limits? And that's what we're going to focus on now. Now, one more thing before starting to do some examples here. If the limit does not exist, or if the limit is equal to plus or minus infinity, then we're going to say that the sequence diverges. Okay? So I will say that the sequence converges only if the limit exists and it's finite. So this number L must be a finite number. If it's plus or minus infinity, the limit exists, but we do not consider it as convergent. Okay, so we have to be very careful here. The limit must be finite and it should exist, so you only have one limit. This is a very important theorem here, and the purpose of this theorem is to give us a tool on how to compute the limits. Okay, now we know the limit of sequences. We know how to compute the limit of a function. Okay, but how do we compute the limit of a sequence? Well, it turns out that it's very similar. So if we know that the function f of x, if limit of f of x when x approaches infinity is equal to L, and if f of n is equal to a sub n, then the limit of the sequence will be the same as the limit of the function. Here's what I mean by this theorem. We know that limit when x approaches infinity of 1 over x, we know that this is equal to 0. Now, if I take an to be 1 over n, okay, so you can see here that if I call this f of x, I'm just trying to mimic the same notation in the theorem. So this is L in this case. So if limit of f of x is equal to L, and if f of n is equal to an, which is the case here, then this implies that the limit of an when n approaches infinity is equal to 0 in this case, which is L. So that's why the limit here is equal to 0. The same reason the limit here is equal to pi over 2, because we know that limit when x approaches infinity of tan inverse of x equal to pi over 2. Okay, so this is one of the limits that you should know. Now again, when you learn the limits in Calculus 1 for functions, you know that if you take the limit, if the limit of f is equal to L1, if the limit of g is equal to L2, then you can use some arithmetic for the limits. The same thing is true here. So if I know that the limit of an is equal to a and the limit of bn is equal to b, then the limit of the sum is the sum of the limits. The limit of the product of this difference is also the same here. If you multiply by a constant, you can move the constant outside. The limit of the constant is the constant itself. So very similar to the usual properties of limits that you have seen before. Limit when n approaches infinity of an bn is equal to ab, so the limit of the product is the product of the limits. The same thing goes for the quotient. Just be careful here that the denominator has to be non-zero. And here in these two examples, c is a constant. So what I mean by a constant here is something that does not depend on n. Let's take a look at these examples, and I'm going to be using the same the properties that we had in the previous slides. So for this one, for limit of an when n approaches infinity. Why I'm trying to do this? Because the question is determine whether the sequence converges. So if I have to say this, then I have to take the limit when n goes to infinity. Now, if my answer is a finite number, okay, then it's convergent. Otherwise, I will say it's divergent. So that's equal to the limit of, or the limit when n approaches infinity of 5 minus 3 over n squared, equal. Then we will be able to do these quickly. There is no need to do this whole setup that I did before, which means the following. I know that the limit of the difference is the difference of the limits. Okay, so what I do first here is I try to find the limit of this. What happens to this when n goes to infinity? Since this is a constant, then this is going to go to 5. And then I look at the next one, next term. Now the next term is 3 over n squared. This is very similar to considering the function f of x equal 3 over x squared. I know that this goes to 0 as x approaches infinity, and by the theorem we stated earlier, this means that this sequence is going to approach 0 as well. So as a result, my limit would be 5 minus 0, which is 5. This means that the sequence, so then an converges. Okay, and it's convergent to, and limit of an when n goes to infinity is equal to 5. So that means when n gets really large, the values of the sequence will be very close to 5. So this is the first example. Now for the second example, I want to find the limit of a bn when n approaches infinity. So limit of bn. Now before writing this, let's take a look here. I don't know if you know that, but in general, the exponential functions are much they grow much faster than the polynomial function. So even if I have in my denominator n to the power 100 or n to the power, any other number, 2 to the power n will be the for when n is really large. Okay, but to see why this is true, I can do the following. Limit of 2 to the power x of x over x squared when x goes to infinity. I'll tell you why I'm trying to use the function now. First of all, if you try to find the limit of this, this is going to be 2 to the power infinity, which is infinity, over infinity squared, which is infinity as well. Now the problem is when you don't have a continuous domain, and that's what we have really for the sequence, because this for the sequences, the n is not over r, so I cannot take derivatives. Okay, so in other words, I cannot apply the L'Hopital's rule. So what I do here is the following. I'll try to find the limit of this function, and if the limit of this function goes to anything, then that would be the same answer for the limit of bn. And I'm trying to use the function here because I will be using the L'Hopital's rule to show you how I find the limit. First, I have to make sure that this is an undetermined form. So you cannot apply L'Hopital's rule unless you have an undetermined form. And infinity over infinity is one of them. So I use L'Hopital's rule, limit of 2 to the x over x squared when x goes to infinity. This is the limit when x goes to infinity. Okay, I will put h here. That means at this step I'm applying L'Hopital's rule. I'll take the derivative of the numerator. Derivative of 2 to the x is 2 to the x multiplied by ln of 2. The derivative of x squared is 2x. Okay, now again I still have the same problem, which is infinity over infinity. So I can apply the L'Hopital's rule one more time. So this is going to be the limit when x approaches infinity. 2 to the x times ln2, and you have another ln2 already there, over 2. Well, this is infinity divided by 2, which is infinity. Okay, so then limit of Bn when n approaches infinity is infinity. This implies that Bn is divergent or diverse, okay? Because the limit is not finite.